Hello, dear friends, students. Many of the solutions regarding with moment of inertia, they've been discussed long back with the students. But again, every of the discussion now, it was eluded because of the time. Yesterday, because of the heavy and the beautiful rainfall, the things are recollected back. So it's good to make a video about it. What was it all about? Of course, it's the moment of inertia of a square with respect to the axis along with the diagonal, and the moment of inertia of a square with respect to the axis along with perpendicular bisector of the opposite sides. I had to prove that they are equal. Lot many of the other things were needed to prove this particular fact. Now again, by common sense, or maybe because of the mass distribution with respect to both of the axes, it looks that the moment of inertia is same. But of course, there has to be a precise mathematical proof for all of it. So we say that we'll go for it. Again, if you consider the moment of inertia with respect to the diagonal, it looks that it has been divided into two of the right angle triangles. So it's better to start with moment of inertia of a right angle triangle. So I won't consider any specific right angle triangle, but I'll consider a general right angle triangle. So what is this all about? I take a right angle triangle like this, and I'll consider an axis along with any of the perpendicular with respect to any of the perpendicular side. Let's say it's this, and I'll try to find the moment of inertia of this right angle triangle with respect to this particular axis. How exactly the procedure will be, I'll take a small part of this triangle. I'll find the moment of inertia of this strip with respect to the particular axis. A strip has thickness dx. It is at a distance x from the axis with respect to which we are finding the moment of inertia. The perpendicular sides, the lengths, I'll take it as maybe A and B. And I'll try to find the moment of inertia of this right angle triangle with respect to the axis along with the side A. Again, I'll take rho as a surface density, which is mass upon area. Area of this right angle triangle, of course, we know it's half of A into B, as simple as that. All now it's needed now to how to find the mass of this particular strip. For this, I'll need this length y, and the thickness dx is been given already, or we have taken the thickness as dx. So by using a simple similarity, I'll try to find the length y. So how we do that? I'll consider the similarity of this triangle and the bigger one, this one. So just in case, suppose if I say this is x, this is b, so this is gonna be b minus x. So I'll get b minus x upon b is equal to y upon a. So I'll get y is equal to a upon b into bracket b minus x. So the area, small area of the strip will gonna be y dx, which is a upon b, b minus x into dx. That will gonna be the area. The mass of that will gonna be a upon b, b minus x dx into rho. It comes as this. So then the moment of inertia of that particular strip will gonna be di is equal to integral of x squared dx. So let's substitute the values for dm, and of course the strips will start from the axis with respect to the side A, and it will end up to here. So it'll be along with the length B. So I'll put the limits of integration as from 0 to B. So let's do this slowly and steadily. dm is substituted as this. So how we're going to move on with, maybe it looks as I will be from 0 to B, x square dm I substituted as a upon b, b minus x rho dx as is. So a upon b comes out to be as common, rho comes out to be as common, and integral 0 to b will stay as usual. Bx square minus x cube dx I have to integrate. So how that will gonna be? Of course, it's not that big deal. So let's do this slowly and steadily. So a rho upon b stays as it is. This will gonna be bx cube upon 3 and x fourth upon 4. And the limit of integration, I'll put them as 0 to b. So a rho upon b, and this will gonna be b fourth upon 3 minus b fourth upon 4. And the net answer comes to be as a rho upon b into bracket b fourth upon 12. Means I'll take an LCM, everything about the fractions, and the answer comes to be as this. So finally, we get the moment of inertia as capital I as half of a b rho. This one of the b gets nicely cancelled, and we'll get b cube. One of the b has been taken out, so all remains inside is b square upon 6. This half a rho b, half a rho b, it will be the total mass of this right angle triangle. So mb square upon 6, that becomes a moment of inertia of a right angle triangle. So all it matters, I think, is with the length b, which has been distributed from the axis of rotation of a right angle triangle, which contributes to its moment of inertia. This length a, along with which the axis is there, it really doesn't matter. But of course, that will be incorporated in this mass, which contributes to mass. So the formula for the moment of inertia of a right angle triangle along with the axis A, to which the length perpendicular is b, is given by mb square upon 6. So again, if you consider the moment of inertia of a right angle triangle with respect to the axis b in the other case, it must be given by the expression I is equal to m a square upon 6. So let's say suppose if the axis is this and the mass will be distributed along with the side A, then the expression changes maybe as this. So this was just the beginning. Now with the whole of it, we'll try to go for the moment of inertia of an isosceles right angle triangle. Isosceles triangle. What is an isosceles triangle? Maybe also two of the sides are equal. This one and that one. This is the base, and the axis considered to be as a perpendicular to the base as this. And we have to find the moment of inertia with respect to this particular axis. So again, all I should say that this particular axis, whatever we drew just now, it divides the isosceles right angle triangle into two right angle triangles. So I'll call the equal lengths as maybe A and the base length to be as B. Not like this. Let's try to be a little bit decorative. So I'll say this is B by 2 and B by 2. So I'll find the moment of inertia of the left-hand side right angle triangle and right-hand side right angle triangle I1 and I2s, and I'll add them, or maybe I'll double any one of them. So I1 I'll find by using m by 2, mass of the left hand side rectangle, I'll take it as m by 2. B square will gonna be b by 2 square upon 6. So whole it happened as m b square upon 4 into 8, and 8 into 6 will be 48. So then the moment of inertia of the entire isosceles triangle will gonna be I, which is 2 of I1, which is mb square upon 24. mb square upon 24. That's how it comes. The moment of inertia of an isosceles triangle with respect to the axis, this axis, whatever is that, which is the perpendicular bisector of the base or perpendicular bisector of the third side, or I meant to say the side which is not included into the equal sides. It comes to be as mb square over 24. Now let's get back to the moment of inertia of a square with respect to the axis along with the diagonal. So maybe I should say this. So again, we can observe that the square now it's been divided by, square is now it's been divided into two right angle triangles, isosceles right angle triangles, or I should say just an isosceles triangle with the side A and the unequal side as a root 2. So this will gonna be a root 2 divided by 2, and again this will gonna be a root 2 divided by 2. The diagonal of a square will gonna be a root 2, as simple as that. Means lower standard geometry, whatever it says as a root 2 divided by 2. So it will gonna be a upon root 2. This will gonna be a upon root 2, and that will also will gonna be a upon root 2. A upon root 2 and a upon root 2. I'll take the mass of this upper triangle as m by 2. So the moment of inertia only of the upper isosceles triangle. Actually, it is an isosceles right angle triangle, but let's not go into too much of the specialization. Just I'll write I1 as the formula goes as mb square, mb square over 24. So m by 2 square. This b used to be the length of a base, or maybe the side which is not included into the equal sides. So mb square over 24. So b, I'll take it as a root 2. And the 24 stays 24. This 2, why m by 2? Because we are considering only the half part of the square. The entire mass of the square, I'll take it as capital M. So let's simplify this particular expression. So I'll get m a square 2 upon 2 into 24. 2 nicely gets cancelled. And I'll get ma square upon 24. Must be the formula for the moment of inertia of isosceles triangle, which is shaded with a red shade. The total moment of inertia of a square, including even the second isosceles triangle, is going to be the double of this. So that will be ma square upon 24 into 2. So it is ma square upon 12. So basically the total moment of inertia of a square with respect to the axis along with the diagonal is given by I is equal to ma square upon 12. The answer has come as this. Now we'll try to find the moment of inertia with respect to the axis, which is perpendicular bisector of the two of the sides. So this is again the square, and we are finding the moment of inertia with respect to this particular axis. I can also generalize the case of, sometimes the people tend thinking too much about their knowledge, which I tried doing it on yesterday, but now I think the things are getting more and more clear. Yeah. We are utilizing the formula of a moment of inertia for a rod with the length L by 2 and L by 2 or maybe the total length as L, instead of going into, I'll say, too much of the specialized cases. I'll just take the entire length as L, mass as M, and the moment of inertia of this, it comes as ml square by 12. So moment of inertia of a square with respect to the axis along with the perpendicular bisectors of the two of the sides is given as ml square by 12. And even the moment of inertia of a square with respect to the axis along with the diagonal, it comes as ml square, ma square by 12. So here again, the length, it's supposed to be a itself, which is again ma square by 12. And from the two of the expressions, it nicely looks as two of the moment of inertia are same. By common sense, of course, maybe you'll try to make a sense, but still here is an detailed mathematical proof. Thank you, and thank you very much.